Go ahead.
Today we are drawing the Lewis structure of H2S. So to start this, we're going to start by counting the number of valence electrons. Hydrogen has 1, and since there's 2 of hydrogen, you multiply it times 2. And sulfur has 6, so you add them together and you get 8 valence electrons. So you put the sulfur in the middle because it's the least electronegative, and you connect it with bonds to hydrogen. And hydrogen never has any lone pairs attached to it, so the remaining, so there's 2 here, 2 valence electrons here, 2 valence electrons here. The remaining 4 will go on the sulfur as lone pairs. So it satisfies the octet rule, and that's how you draw the Lewis structure for H2S. So for H2S, it is nonpolar, and its electron pair geometry is tetrahedral because there's 2 bonds and 2 lone pairs coming out of it, which equals 4. And the shape is bent, which means that the ideal bond angle is 120 degrees, and it'll look something like this.
Hello, so today I'm going to teach you guys how to do the Lewis structure for xenon difluoride. Alright, so here's xenon difluoride. First we're going to find the number of valence electrons that is in this compound. So xenon has 8 and fluorine has 7. So we're going to do 8, and there's only 1 xenon, so just 1. And it's going to be 8 plus the 7 from fluorine, but there's 2, so we're going to do 7 times 2. And this is going to be 8 plus 14, which is 22 valence electrons. So we have 22 valence electrons in xenon difluoride. Now, what we're going to do is we're going to create the actual Lewis structure. Now, xenon is going to go in the middle of the Lewis structure because it is the least electronegative. So, I'm going to put the xenon in the middle, and the fluorines are going to go on either side. Now we're going to connect these two, and when we connect them, we understand that we've used now 1, 2, 3, 4 of our valence electrons. So we're going to mark that down. We've used 4. Now, we must satisfy the octet rule for the fluorines first. So we've used 2 here, so that means we need 6 more on each fluorine. So we're going to do this by adding lone pairs. It's going to be 3 different lone pairs on each one. So now there's an octet rule satisfied here, and an octet rule satisfied here. So we've added 6 to both sides, so it's going to be 12. So now we've used 16 electrons. So now that we've used 16, we have xenon and xenon to fill now, and we have a total of 22 valence electrons in this compound, which means we have 6 left that we need to distribute to xenon. So we put 2 here and 1 up here, and this is going to be your final Lewis structure for xenon difluoride. So with xenon difluoride, we know that it is nonpolar. It is a trigonal bipyramidal for the electron pair geometry because it has a bond here, and then it has 3 electron pairs around it. Sorry, lone pairs around it. Now the shape is linear. Just looks like this, and the bond angle is 180 degrees.
Today we'll be drawing the Lewis structure for boron trichloride, and according to the periodic table, boron has 3 electrons, valence electrons, and chlorine has 7. So we'll do 3 times 7 since we have 3 chlorine atoms, and we get a total of 24 valence electrons. Now when we actually draw the structure, we'll put boron in the middle since it is the least electronegative, and then we will distribute all 24 electrons following the octet rule for every single atom. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 electrons total, and each atom satisfies the octet rule. Boron trichloride has an electron pair geometry of trigonal planar, and since it is nonpolar and it has 3 structural bond pairs, its molecular geometry is also trigonal planar, and because of that, it has an ideal bond angle of 120 degrees. Today we will be drawing the Lewis structure for Cl03-, and first we'll count the valence electrons. Chlorine has 7, and then we have 3 oxygens, which each have 6 valence electrons, and since we have this negative charge, we have to add 1 electron on for a total of 26 valence electrons. We're going to put chlorine in the middle since it is the least electronegative, and put our oxygens out here, and then we're going to make sure the oxygens satisfy the octet rule. So we'll begin putting our bonds and lone pairs. And at this point we have only used 24 electrons, but every single atom has a full octet, so we're going to put the extra 2 electrons with the chlorine up there since it is the central atom.
Go.
Cl03- is a polar molecule because it has an extra lone pair on top, and it has a tetrahedral electron pair geometry, and since it is polar and it has that 1 lone pair, its molecular shape is trigonal pyramidal, giving it an ideal bond angle of 109.5 degrees.